integrating functions of time, that's what I've headed this one. We have a velocity time graph there, and it's a quadratic function. So if I want to work out the change in displacement, velocity is the derivative of displacement, then I can just integrate. Because it's displacement we're talking about, it'll be the complete integral from 0 to 4. But if I want to work out the change in distance, then I have to split it into above and below. So this is very similar to when we're looking at, are we talking about area under a curve, or are we just talking about the integral? So if it's displacement, it's the straight integral, but if it's distance, we're talking about the area, so we have to break it up. Then we've got our acceleration graph, and I could create that one. Similar thing. If I wanted to work out the change in velocity, it would be the straight integral, whereas change in speed would be the area. So we've got to break it up. When's it above, when's it below? So when we are drawing these derivative graphs, so we start with a function, we might want to draw the first derivative, we want to draw the second derivative. When we talk about motion, we're assuming the function's displacement, first derivative is velocity, the second derivative is acceleration. So how can we tell? What do we look at? If I've got a stationary point on the displacement graph, well, that means that the first derivative is 0, so I should see an x-intercept on the velocity graph. If I've got an inflection point on the displacement graph, well, an inflection point means that the second derivative would be equal to 0, which means we have an x-intercept on the second derivative graph. But if that is an x-intercept, then the one before it must have been the stationary point, because when we got the stationary point, it went to x-intercept. So I know on the velocity graph I should see a stationary point. If the function, so displacement graph, is increasing, well, that means the derivative is positive, so the velocity graph should be positive. Decreasing, it should be negative. When it's concave up, that's now telling me that the second derivative is positive, therefore the first derivative must have been increasing. So I should see that. There we go. And concave down, similarly, second derivative would be negative, but it means the first derivative is decreasing. So if we have to draw these graphs, they're the sorts of things we can look at. The graph type. If I've got a horizontal line, if I'm integrating it, then I must get an oblique line, because a horizontal line would be a constant. Integrate a constant, you get a constant times x. If you differentiate it, you're going to be talking about the x-axis, or whatever the horizontal axis is called, because you're going to get 0. If you have an oblique line, when you integrate it, you should get a parabola. It's going to be a quadratic function. If you differentiate, it'll be a horizontal line. And if you have a parabola, then when you integrate, you should see a cubic. That cubic will end up inflecting at the turning point, because you could have a stationary point at the turning point, therefore you would have an inflection point. And it will be an oblique line when you differentiate. So, key things to remember here when we're talking about these graphs. Integration is area, we know that. Integration is area. On a velocity graph, area would be distance, the integral would be displacement. On an acceleration graph, area is speed, integral is velocity. Let's have a look at a couple of HSC questions. We have a trig function here for velocity. At what times is it at rest? The standard sorts of questions. Well, I know it's at rest when the velocity is equal to 0. It's just pretty much solving this trig equation. Cos t is a half. So if you're first quadrant or the fourth quadrant, acute angle pi on 3. Notice the pi. And we use radians. Whenever we're doing calculus and trig, radians is the measure we use. So t is pi on 3, 5 pi on 3. And this is why we must use radians. Because if I didn't use radians, that pi on 3 would be a very different number. It would be 60. And we'd be saying, well, it stops after 60 seconds. No, it doesn't. It stops after pi on 3, which is 3.14 divided by 3, so a bit over 1 second. Very different answers. And so got to be in radians. So particle is at rest after pi on 3 seconds, and then again after 5 pi on 3 seconds. What is the maximum velocity of the particle? Well, I'm going to use the graph now. I mean, I could use calculus, but I've got a trig function. And when you start talking about maximums and minimums of a trig function, just thinking about the graph's a lot easier, because I know that just the trig part, forget about the shifting at this stage, that's got to go in between -4 and 4. So if I shift the whole thing up 2, which is what we've done here, it goes between -2 and 6. Ah, well, the maximum velocity therefore is 6. And that's going to be a lot quicker than using calculus to find it. Sketch the graph. Oh, well, it's essentially asking me to draw a trig function. Amplitude, 4 units. Shifted it up 2. It's upside down because it was a negative cos graph. Period is 2 pi. I'll mark my divisions off every pi on 2. There's my axes. We shifted up 2, so I'll just put a dotted line in there so I know where I'm winding my curve. I will start at -2. Cosine function, normally I would start up at the top amplitude, but this is a negative one, so I start down here. And then the pattern is, goes to the axis, then up and down. Bingo, there's my graph, velocity time graph. Calculate the total distance. Make sure you read correctly. Are they asking distance? Are they asking displacement? So you know, am I finding the area or is it just the straight integral? Because when we go from 0 to pi, you will notice it changes. So 0 to pi for when it's above and when it's below. Okay. It's actually at pi on 3. I didn't mark it there, but it will cut there at pi on 3. We found that out because we did have a question, didn't we, where velocity was 0. So we know that's pi on 3. Okay, so I've got to break it up. 0 to pi on 3, and then pi on 3 to pi for the 2 bits. Okay, and you'll notice I've done the technique of, oh, well, I'll just flip the integrals and I made it a positive here. That way the lower limit's pi on 3 for both. Just saves a little bit of substitution. So with the top ones, sub in 0, sub in pi, take away 2 of the bottom ones when I sub in pi on 3. And it's a weird answer. I've left it as an exact answer. A physics teacher would hate it because they can't handle things like this. They want a number. We're maths, I can handle that, that's a number. 4 root 3 plus 2 pi on 3 metres. Don't ask me how big that is, that I couldn't work out. I would have to go to a calculator. 2004, they gave us an acceleration time graph. Again, moving along the axis under this. Write down the time for which the velocity is a maximum. We've got an acceleration time graph. So when's the velocity a maximum? Well, velocity, I know, is the integral of acceleration. So it's asking, when is this integral a maximum? Well, it's going to be at t equals 2. Because if I'm talking about the straight integral, as I move, I've got positive, 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 so it's getting bigger and bigger and bigger because I'm adding more area. But once I go past 2, this is now negative. So I'm talking about the straight integral. This is now going to take away from the area that I've created, and it never goes positive again. So it must be at t equals 2 that velocity, because that area will be a maximum at t equals 2. Of course, the other way you could do it, you could say, well, I know it's a maximum when the rate of change is equal to 0. So v to t is equal to 0. When is acceleration equal to 0? Again, I could just look at the graph and go, oh, well, that's 2. That's where it is. So whichever way, but it's at 2 seconds. At what time during the interval is the particle furthest away from the origin? So now we're talking about displacement. When's the furthest away? Okay. When's displacement a maximum? Well, it's going to be a maximum when dx to t is equal to 0. Now, velocity is the integral of acceleration. We said that. So we're basically solving, when is that integral equal to 0? All right, well, we're going to increase the area, increase the area, increase the area, increase the area, and then we're going to start taking away. Basically, we want to know, when is this area below going to be the same as the area above? At what point? Well, it's a symmetric graph, so that makes life a little bit easy. So by symmetry, well, if it took 2 seconds to get there, it must take another 2 seconds, and the area is going to be the same. T equals 4, so 4 seconds. 2007, the graph was a little bit more interesting, you'll see. This time we have a velocity time graph with all these interesting curves and what have you, but we do not know the function itself. They haven't told us that. They've given us particular coordinates, and once it goes past t equals 6, it's just a constant velocity. Oh, you would have loved this HSC, using the trapezoidal rule, because we don't know the equation of the graph. So we can't actually physically integrate it. We can estimate using the trapezoidal rule the distance between, going from 0 to 4. And that's why they've given us the coordinates of these points, so we can get some values to put into the trapezoidal rule. Remember trapezoidal rule, h over 2, y naught, yn, 2 times all the others. So I'll draw up a table of values. There's only 3 values that I know, so they're the ones I'm going to use. It'll be 1 times the n ones, 2 times the one in the middle. Putting it all into our trapezoidal rule, 7 metres. Well, it's an estimate, but that's going to be my estimate, about 7 metres. The object is initially at the origin, during which time is displacement decreasing. So when is the first derivative less than 0? When is velocity negative? Well, hang on, we've got a velocity time graph, so we can just read that straight off. Well, it's negative after 5 seconds. So that's when it'll be decreasing. Estimate, and of course we can only estimate because we estimated how far away it was in that other one, but estimate the time at which the object returns to the origin. When does this return to the origin? Okay. When is displacement equal to 0? So similar to that last question. So it's saying when is the integral of velocity equal to 0? When is the area above equal to the area below? Now this one's a little bit more interesting. How are we going to do these areas? Now, I know there's some sort of symmetry happening from 4 to 6. So these 2 triangles will cancel each other out. I want to know, when does this rectangle after 6 have the same area of this interesting curve shape? That's essentially what we need to now work out. But we did estimate that. We just estimated that to be 7. So when is that rectangle got an area of 7? I've called it area 4. Maybe because it's the 4th section there. But, yeah. So 5 times A, I'm just saying how far after 6, that's got to equal 7. So A is 1.4. I'm estimating it to be around 7.4 seconds. But that's going to be the same. Now this one's fun. Sketch the displacement time graph. There's our velocity time graph. I always like to draw these underneath each other or above each other depending, so I can just transfer information straight down. So I'll put my axes in here for displacement time. I've labelled in some key points that we have worked out. 7 was important, 9.5 becomes important, and then our different times there. So watch carefully. Here's how I put this together. We know the object is initially at the origin, so let's plot that point in. There it is. We estimated that when t equals 4, displacement was 7. So let's put that point in. By symmetry, at t equals 6, it's got the same displacement, because that's when these 2 triangles match their areas. So at 6, I'll plot that point in. The area of the triangle, that's where the 9.5 comes in. That triangle has an area of 2.5, so I knew the displacement went another 2.5, so it goes up to 9.5. Plot that point in. Returns to the origin. We worked it out. We estimated at 7.4. Plot that point in. Now here's the tricky bit. What to do between these dots? A is an important point here. Looking at this graph, I can see the velocity is steeper between A and B than it is between 0 and A. Therefore, it's going faster. Therefore, it should travel more distance in that time. So when I plot this graph, then it should be closer to the t-axis at 2. It's not going to be in the middle, because it's going to cover more in the second 2 seconds. So I'm going to put it lower down than the middle. Again, I don't know exactly where, but I'll put it there. It's just an estimate. Oh, they told me when t is greater than 6, the velocity is constant. Okay, that means I know that's a straight line. Horizontal lines become oblique lines. I've got 2 points on that line. Excellent. I've got that part of the graph. It's going to be a straight line. I've now filled in the rest. Now, oops. How did I fill in the rest? Well, I know I've got to go through these points. This is an oblique line from B to D, and when I integrate the oblique line, I get a parabola. So I know this must look parabolic. Here, I don't know the function of this curve. It's just some sort of curve, but logically when I integrate the curve, I'm going to get a curve. some polynomial, for instance. I'm going to get another polynomial. I just got to make it go through these points, and I've made it concave up, because how on earth could you draw a concave down one going through all those points? Couldn't do it. So that's what I reckon the graph looks like. Okay. 2005, velocity time graph they gave us again. At what time is the displacement a maximum? When is it a maximum? So again, what are we saying? Well, maximum is when the area is most positive. It's also when velocity is 0. We've got a velocity time graph. So I can just read off my graph. T equals 2. Displacement is a maximum. At what time does the particle return to the origin? So again, same sorts of questions. When is displacement equal to 0? When is the area above the axis equal to the area below the axis? Okay. Well, that first section there is a rectangle, its area is 2, I can work that out. Don't know what the area is of that section there, but by symmetry, looking at it, I think that's meant to be the same. And then we've got this one here. I want the area above to be the same as the area below, so I now want to know when is this rectangle going to have an area of 2. That's what I want it to be. In other words, how wide is that rectangle? Okay, 2 times W is got to equal 2, W is equal to 1, 4 seconds. After 4 seconds, it's got to go back to the origin. Draw the acceleration graph this time. So we have a velocity graph. This time we're going to draw acceleration. In other words, draw the derivative graph. Okay, let's put it underneath, label some key points. Here's how I do it. Well, I'm going to differentiate a horizontal line. Differentiate a constant, you get 0. So in other words, we're going to be on the x-axis at those 2 points. So we'll just travel on the x-axis. From 1 to 3, look, I don't know. So I'm just guessing. But I'm saying that's a cubic. Kind of looks like a cubic, does that sort of thing. So I'm calling it a cubic. It inflects at 2. So now I'm going to get a stationary point down here for that. And it's decreasing, so I know it's always going to be negative. Differentiate, get the parabola. Okay, I'm drawing one in. How far down? I don't know. I haven't got enough information. So I'll just draw that. From 5 to 6, and this is the one where I really am taking a leap of faith. But looking at the picture, it kind of looks to me that that shape's meant to look the same as this shape. Yeah, it's reflective. So if I assume that was a cubic, I'm going to assume this is part of a cubic as well, which means I should get something that's parabolic when I do it. But this time it's increasing, so it's going to be positive. So yeah, it should really look the same, but it's meant to be half of a parabola as we go up there. So I'm going to make it look like that. Yeah, weird graph, but that would be my graph. I can see you get to play with some of those.